The way it works is tricky, but it's not magic. It's definitely something that you can wrap your head around, and it's not impossible to do so. My goal is that by the time we're done talking, you'll have a pretty crisp picture of how it works. Bayesian inference is just guessing in the style of Thomas Bayes, who was a nonconformist Presbyterian minister. He wrote a couple of books, one about religion and one about probability. So Bayesian inference is just guessing in the style of Bayes. So to illustrate it, imagine that you're at the movies and someone drops a ticket. You pick it up and you can see them from behind. You know they have long hair, but you don't know whether they're a man or a woman, so you have to make a guess. Based on what you know about the attendees at your movie theater, you might say, "Excuse me, ma'am, is this your ticket?" Now imagine instead that this person is standing in line for the men's restroom. Knowing this extra piece of information, you might make a different guess. Bayesian inference is a way to capture this common sense knowledge about the situation and help you to make better guesses. So to put numbers to this dilemma at the movie theater, let's assume out of 100 women at the movies, 50 have short hair, 50 have long, and out of 100 men at the movies, 96 have short hair and 4 have long. In this case, we can see that there are definitely more women with long hair than men with long hair. So it's a safe bet to assume this person's a woman. Now we just made a subtle assumption that there are about the same number of men and women at the movies. This assumption no longer holds when we move to the men's restroom line. Here, let's say there are 2 women out of every 100 people and 98 men, maybe women keeping their partners company. There's still one with short hair and one with long hair. It's still half and half long and short hair, but now there are 4 times as many men with long hair than women with long hair in this group. Now the safe money is to bet that this person is a man. So to draw this a little differently, out of 100 people at the movies overall, we'll make this assumption explicit that 50 of them are women, 50 of them are men, so this is how the different categories break down. In the line for the men's restroom then, they break down a little differently. So to translate this to math, the probability that a person is a woman is the total number of women divided by the total number of people, 50%. Similarly for men. Moving to the men's restroom line, the probability that someone is a woman is 2%, 98% for men. Now, Bayes' theorem is a little bit tricky, so to be very precise, we're going to have to talk math. So if you bear with me for just 3 probability concepts, we'll lay the foundation for presenting Bayes' theorem. The first one is conditional probabilities. If I know that a person is a woman, that's the condition, what's the probability that that person has long hair? So it's written as probability of long hair given that a person's a woman. So to get this, we just divide the number of women with long hair by the total number of women, 50%. And this doesn't change whether there's 50 women in your group or 2 women in the group. Still, if we know that a person is a woman, the probability that they have long hair is 50%. We can do the same thing with men. Probability that someone has long hair given that they're a man is 4%. So conditional probabilities, if I know that B is the case, what's the probability that A is also the case? This is not, you can't reverse B and A and have this be true. So for instance, if I know that the thing I'm holding is a puppy, what's the probability that it's cute? The probability is very high. If I know that the thing I'm holding is cute, what's the probability that it's a puppy? Well, it might be a puppy, it might be a kitten, it might be a hedgehog, it might be a small human. There's lots of things that it could be, so the probability there is less moderate. So these things are not interchangeable in conditional probabilities. Now, concept 2, joint probabilities. So what's the probability that a person is both a woman and has short hair? So to calculate a joint probability, you first find their conditional probability. Well, if I know that they're a woman, what's the probability that they have short hair? And then you multiply that by the probability that they're a woman. So in this case, 0.5 times 0.5, we get a 0.25, which is exactly what we knew it was going to be. And the same is true for all of our different conditions. So we can do this for the men's restroom too. The probability that someone is a man and has long hair, 4%. Someone is a woman and has long hair, 1%. Joint probabilities are different than conditional probabilities. Here, the probability that A and B is the case is the same that the probability that B and A is the case. So the probability that I'm having a jelly donut with my milk is the same as the probability that I'm having a milk with my jelly donut. These two conditions, these two situations are identical, so we can swap the order. And finally, concept 3, marginal probabilities. If I wanted to say figure out the probability that someone has long hair, I just add up all of the different ways that someone can have long hair. They can be a woman with long hair or a man with long hair. In the men's restroom line, that's a 1% probability plus a 4% probability, or a 5% probability overall. And you can do the same thing for short hair, 95%. Now, this last concept finishes our foundation. We can get to what we really care about. We know that this person has long hair. What's the probability that they are a man or a woman? This is a conditional probability, but it's the reverse of the one that we know. And we don't know how to answer this yet. So, this is where Thomas Bayes comes in. He noticed something really cool. You can calculate the joint probability that someone is a man and has long hair using the formula we saw before. And you can also calculate the joint probability that someone has long hair and is a man. Now, these are different formulas, but remember, joint probabilities don't care about the order. So these two things are equal, which means the stuff that they're equal to on the other side are also equal to each other. And we can do a little algebraic sleight of hand. And now we have a formula for what we want to know. If someone has long hair, what's the probability that they're a man? And we have this expression to the right. We can genericize that with A's and B's, and now we have Bayes' theorem, one of the top 10 most popular math tattoos of all time. So using this formula, we can go back to the movie theater and plug in what we know. We know that the probability that someone is a man. We know the probability that if they're a man, they have long hair. And we know the conditional probability, the marginal probability that someone has long hair, which is just the probability that someone's a woman with long hair plus the probability that someone's a man with long hair. And we plug all that in, and we can say if someone has long hair at the movie theaters, there is a 7% chance that they are a man. Similarly, 93% chance that they are a woman. Now, if they're in line for the men's restroom, because some of those probabilities change, that conditional probability changes. If someone's in line for the men's restroom and has long hair, there's an 80% chance that they are a man. And this is consistent with what we saw before. We know that there are 4 men and 1 woman for every 100 people in line for the men's restroom that have long hair. So 4 out of 5 long-haired people are men, 80%. It all adds up. So this example shows the mechanics of how to get Bayes' theorem and how it works. In practice, it's usually used a little differently. So to show this, we'll have to do a little bit of a detour and first talk about probability distributions. You can think of probability like a pot with just 1 cup of coffee in it. You can fill up, if you just have 1 cup to fill up, you can fill it all the way to the top. But if you have more than 1 cup, you have to share it around or distribute it. And you can share it in any proportion you want. So for instance, if we're representing the number of men and women at the movies, we could share it 50-50, but it'll always add up to 100%. We could even share it further into different categories. So here we see the joint probabilities of all of our 4 different categories that we were working with. And you can see that this is just another representation of the distribution representation that we were looking at before. Now usually when we look at this, they're side by side, probability instead of percentage, and shown in a histogram like this. It can be really helpful to think of these as beliefs. So for instance, if I flip a coin and hide the result from you, you might half believe it's heads and half believe it's tails until I tell you what it is. If I roll a die and hide the result from you, you might believe about 1/6 that it's a 1 or a 2 or a 3 or 4 or 5 or 6 until I show you the result. So these are what you believe. Probabilities can represent what you believe about something before you measure it. Similarly for Powerball tickets, and even for things that are more complicated, like let's say the height of adults in the United States in centimeters. You might believe that there's a very small chance that they'll be over 210 centimeters and a smallish chance that they're less than 150 centimeters, and then assign various amounts of this belief to all of the ranges in between. It still adds up to 1. It's like a bunch of cups of coffee lined up in a row, and you put a little bit in each one. The cups in the middle have more. And it shows how your belief about some individual is distributed before you've actually measured them. Now you can take these bins and chop them more and more finely, again and again, and if you keep doing this, you can get to something that's actually perfectly smooth. So it's as if you had an infinite number of very tiny cups and you put a tiny bit, infinitesimal amount of coffee in each one. At this point, it's probably no longer helpful to think of it in that terms, but just thinking of it as a continuous distribution, showing for all these heights, where am I placing my bets? What do I believe and how much? So once you have your beliefs, you can use it to answer questions about typical heights, the average, the median value, the most common value or the mode,